We talk about impulse momentum, and impulse momentum are really good for problems that involve force, velocity, and time. Okay, so no acceleration, no position. Okay, so we'll start with Newton's second law, knowing that acceleration can be written as the time derivative of velocity. Okay, then doing some separation of variables to solve this differential equations. I bring dt over to this side, so I have f dt on one side and then m dv on the other side. Okay, well, m is going to be constant for most of the problems that we're dealing with. Bring that outside the integral, and I just have the integral of dv, which is just simply the change in v. Okay, rearranging that equation, basically bringing mv1 over to this side, I basically get mv1 plus the integral of f dt equals mv2, which is essentially the linear momentum, the initial linear momentum, plus the linear impulse, which is a force times a time, equals the final linear momentum. Again, no acceleration, no position. This just deals with force, velocity, and time. Okay, this is a vector equation, so there are, this can be applied in all three directions. Okay, so unlike energy, which was a scalar equation. Okay, so you have momentum impulses in specific directions. Okay, let's talk a little bit about impulses. A common one is a constant force that we've dealt with before. So if the force is constant, then this integral becomes very easy. F comes outside the integral, and I'm just left with the integral of dt, which is just the change in t. So that the impulse of a constant force is just that force times the change in time. Okay, now, for certain problems, we have things that we call non-impulsive force, and these are forces that occur over a very, very short time, and they can be neglected. Now, we can't ignore very large forces, such as like a hammer hitting a nail. What we're more looking at is when a hammer hits a nail, yes, there's a large force. It occurs over a very short time, but those smaller forces, such as gravity, it's much smaller than the impulse of the hammer hitting the nail. Okay, so we can neglect gravity over that short period of time because it is so vastly outweighed by the very, very large impact force of the hammer hitting the nail. Okay, so there are certain, and a lot of times it's gravity that we're neglecting. Okay, when we have short impulses occurring, okay, those smaller forces can just be neglected. Okay. As with every other type that we've looked at, Newton's second law, energy, system of particles, right? I can take all of the particles, sum up all of their momentums, all of the external impulses on them, and set that equal to a final momentum of all of the particles. So just like we've done before, you can take them particle by particle or as a system by summing them all up. Now, conservation of momentum. Okay, remember conservation of energy occurred when there was only conservative forces. Conservation of momentum occurs essentially when there are no impulses, or more specifically, the external impulses equal 0. So basically, if the delta f dt goes away, then I'm just left with my initial momentum equals my final momentum. Okay, now this is most useful when we talk about impact problems, where you've got two particles colliding. Okay, and if those two particles collide, if I take them as a system, okay, the impulse in between them is internal to the system. That is, because of Newton's third law, one particle hits the other with the same amount that the other particle hits the other, and it goes away. Okay, so the external impulses have to equal 0 for momentum to be conserved. So the best way to deal with that is, hey, if there's an impulse, somehow get that to be an internal impulse, then you have conservation of momentum. Okay, so again, impulse momentum, force, velocity, and time, initial momentum plus the impulse equals final momentum. If there are no external impulses, the momentum is conserved.